Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the smallest substring containing. I really like this question because it uses a pretty cool technique that you're going to be able to use for a lot of other questions. And this technique is very intuitive once you see it in action. So the question gives you two strings, a big string and a small string. So in the example in front of me, this is going to be the big string and this is going to be the small string here. And you have to find a substring in the big string, and more specifically, the smallest substring in this big string that contains every character found in the smaller string. Now, there are a few caveats. First of all, if there are duplicate characters in the smaller string, like here there are $2 signs, you need to find a substring that has those $2 signs. You can't have fewer. And the second thing is the substring can have other characters that aren't found in the smaller string. In fact, it can have more characters than the ones here. Like it could have $3 signs, so long as it has at least two. And finally, you don't care about the order of the letters or of the characters. In other words, you are not looking specifically for this string. You are looking for just a substring that has all of those characters in the correct amount. So in the example in front of me, the answer is going to be this, $AXB$. And as you can see, it is this substring here. So this substring here is the smallest substring in our big string that contains all of the characters in the smaller string. Okay, so how do we actually solve this question? The first thing that you might think of is that we need to somehow count all of our characters. We need to count how many characters there are in the big string, or rather, count how many of each character appears, and same thing for the small string. And perhaps the easiest way to do this, or the best way as far as looking up these characters in the future, would be to put them in a hash table. And so admittedly, that's what we're going to start by doing. We're going to dump all of the characters in the small string, at least, which is the target string, what we're looking for. We're going to dump all of them in a hash table that is going to serve sort of as a character count table. So the way it's going to look like is we'll put, maybe in purple, all of the characters. So we have, for instance, the dollar sign here. It appears twice in the small string, so it's going to map to 2. The character A is going to map to 1, the character B is going to map to 1, and the character F is going to map to 1. This is pretty simple, right? You just iterate through the string, and you store every character in a hash table. If the character is already in the hash table, you just increment the value by 1, and so on and so forth. So we've done this for the small string. Now we have this reference here, this hash table, that sort of tells us how many characters we're looking for, and which characters we're looking for. So now this is where the technique that I sort of hinted at the beginning of the video comes into play. We're going to want to traverse this big string, right? As you can imagine, we're going to have to traverse it in some way, and at each character sort of try to see, is this one of the characters in this hash table? How many have we had so far? And so on and so forth. But we're going to do this with 2 indices, or 2 pointers. We're going to keep track of 2 pointers at once. And these 2 pointers are going to serve sort of like a window, or like a sliding window. That's the name that this technique often gets given, the sliding window technique, where the string in between the 2 indices should eventually be that smallest substring that we're looking for. So perhaps the best way to actually demonstrate this or to explain this is by just going through the example. So we're going to start with our left pointer, which I'll put with an L, pointing to the very first character in the big string, and our right pointer, which I'll put with an R, whoops, this is a bad R, an R, pointing to the first character in the big string as well. And what we're going to do is we're going to use this right pointer at first. We're not going to touch the left pointer yet, but we're going to use the right pointer and move it along the string. Just traverse the string with the right pointer. And whenever we're at a character, we are going to keep track of that character in another hash table. In other words, just as here we had this hash table for the character counts in our small string, we're going to have a continuously updated hash table for the character counts in the smallest substring that we're looking for. Okay, so I'll actually write this other hash table right next to our first hash table here. I'll write it in green. And so this hash table here is going to start with A pointing to 1. Because here we're at the right index and we have 1A. That's the only thing we have in this hash table. And so we put the A. Now we move our right pointer to the B. And we add the B here, 1. Now at this point I should take a step back and say, what other checks are we performing whenever we iterate through this string? Because we're not just adding the characters in our hash table. The other thing that we want to do is we want to continuously check if we've actually found a substring between the L index or the L pointer and the right pointer that contains all of the characters in this hash table. And so perhaps the easiest way to do this would be to say, hey, how many characters do we have in this smaller string in general? We have 4. It's basically all of the keys in this hash table. So we have, I guess I could write them, in brown up here. We have the $, we have A, we have B, and we have F. So we have 4 characters, unique characters that we're looking for. And as we're moving this right pointer, whenever we find a character like A or B that is one of our characters, one of our target characters, because it's in the hash table, we can check that it's in the hash table, we can increment the value in our substring hash table here, and we can say, wait a second, is the new character count that we have for this character, so for instance for A or for B, is it equal to the character count that we have for that same character in the smaller string hash table? If it is, then we can kind of keep track of how many characters we've completely found. So like, we have completely found A here. So like, we can keep track maybe, again, like in brown up here, that when our right pointer was pointing at A, we had found 1 unique character completed, because we had found 1 instance of A, and there was only 1 instance of A that we needed. Then we moved R to B, and we found that B was in the hash table, so we made B point to 1. And we saw that 1 is equal to 1. We have the same number of B's in our substring between L and R as we have in our target hash table. So we can update this number here in the top left corner from 1 to 2. We now have 2 unique characters that we've found between L and R. Or that we found it, that we've completed. We found the exact number of those characters. Once the 2 here is going to be equal to 4, we will have found a substring that contains all of these characters, and we're going to be able to perform some extra logic. But for now, let's continue. So we're going to continue moving R to the right. So we move R to point to C. Now C is not in our target hash table. Because C is not in our target hash table, we can just skip it and move forward. D, R points to D. Is D in our target hash table? These are constant time lookups, by the way, because we're using a hash table. No, there is no D. Okay. So let's move to the $. Oh, okay, $. $. is in our hash table. We make it point to 1, because we've got $1. But 1 is not equal to 2. We're looking for $2. Therefore, we're not going to update this number here that tells us how many unique characters we have fully found, right? How many characters have we completely found, unique characters? We don't update it because 1 is not equal to 2. We still need another $sign. So now we move the right pointer again to E. E is not in our hash table, so we can move forward. Move it to F. Okay, we've got an F now. F is in our hash table, so we're going to make F point to 1. So now we've got F pointing to 1, and we know that there was only one F in the hash table. So we can update the number of unique characters that we fully found to 3. 3 is almost equal to 4. Not quite, but it's almost equal to 4. So now we keep moving. Put the R to the next character, which is a $sign. $sign is in our hash table. We already have it here, so we just increment this number. And now we have $2 signs. Now this is good because $2 signs is what we were looking for. 2 is equal to 2. So now we can update the number of unique characters from 3 to 4. And this is where we're going to perform extra logic. Because now we can see, whoa, the number of unique characters fully found is equal to the number of unique characters in the smaller string that we've written up here. Right? And this, remember, was obtained by just looking at the number of keys in our hash table. So instead of continuing to move the R pointer, the right pointer, we're going to now move the left pointer to the right, eliminating characters that we have here. Like, as we move it, we'll eliminate the characters that we're forgetting about. Like, for instance, look, if I move this left pointer to the right here, suddenly we can say, okay, now we need to forget about this A. We need to decrement the character count of A in our hash table here, because this A here is no longer between L and R. But the key thing is we want to find how far inwards we can push L, the left pointer, such that we still have the correct character counts in our hash table. Now here we're going to be in for a disappointment because when we push it once, we lose an A, so this A now here becomes 0. I'll write it in maybe purple so that you can see sort of the difference. A is now 0. We've decremented it because between L and R, there's no longer an A. And so now, because we have to decrement this unique character count here from 4 to 3, and 3 is no longer equal to 4, we're going to stop moving our left pointer. We're going to say, okay, we know that between the left and right pointer now, we're never going to have here all the character counts. So let's move the right pointer back to the right. Now, the key thing we should have done before is we should have kept track of this string. We should have kept track of this substring, starting at A and ending at this $sign, because this substring, when the L pointer was pointing to A, did have all of our characters. Okay, so we want to keep track of that substring because it might be the final substring that we have to return. You'll see in the code that we can do this without actually, like, we don't actually need to store the entire substring. That's going to save some space complexity. It's going to save some time complexity because we won't have to slice this substring out whenever we find one that's good. So what we're going to do is we're just going to keep track of the bounds. We're going to keep track of the fact that our substring starts at 0 and ends wherever this index is. Now, for the purpose of the example, I won't actually write that down, but we'll just count the characters. We know that here there are 1, 2, 3, 4, 5, 6, 7, 8 characters. So we have a substring of length 8 that contains all of our characters. So I'll keep track of that, let's say in the bottom right here, or sorry, bottom left. Hopefully you can keep track, you can see it here, the 8. That is the smallest substring that we've found so far containing all of these characters. Let me undo this, so I'll rewrite the 8. Okay, so now point is, we've moved the L, and we no longer have an A, and we need to move back the R pointer. So we're going to move the R pointer to the right. Now we've got an A. Increment the A because A is in our hash table for the smaller string. Increment the A to 1. And now, look, we're back to the case where we have found all of the characters. So increase this 3 to 4, and we can see, okay, how long is our string here? Now our string is, again, length 8. 1, 2, 3, 4, 5, 6, 7, 8. So this doesn't really matter for example. We don't really necessarily have to update it, but we found another string of length 8 that contains all the characters. So now we're going to move the left pointer. The left pointer is now going to move to C. And so we have to decrement B, right? Because now B is no longer in our hash table. Or rather, we just lost a B by moving the left pointer. So we're going to decrement B to be 0. This means that we decrement the number of unique characters fully found from 4 to 3. And we no longer have, like, this substring here is no longer correct, no longer has all of our characters, so we keep moving to the right. So now we're going to move R to the right here, pointing to X. Is X found in our hash table here? No, it's not. So we're going to move R to the right again. Is B in our hash table here? It is. Right? B is one of our characters, so we're going to increment B from 0 back to 1, which means that now we've found all of the characters again. And remember, the way that we can keep track of this is we have our unique characters found here, which is 3. We just increment this to 4, and we can say, oh, in constant time check, 4 is equal to 4, which was the number of keys in our hash table, which we probably stored in another variable. Okay, so then now we have this string. This string is a correct substring that holds all of our characters. Now this substring has 1, 2, 3, 4, 5, 6, 7, 8, 9 characters, so it's certainly not better than the one with 8. But we can try to make it smaller by moving the L pointer. So let's start moving the L pointer. Move L pointer to the right. We lose a C, but C wasn't in our hash table because it wasn't a character we were looking for, so we don't care. Now you can start to see the technique in action, right? We are suddenly shortening the substring by eliminating useless characters. Move L to the right again. D, useless, because it's not in our characters. So we're good. Now, by the way, I guess I should have written that down. We now had a string of length 1, 2, 3, 4, 5, 6, 7, 8. Now we have a string of length 1, 2, 3, 4, 5, 6, 7. So now we should actually update this number here to 7. And again, you'll see in the code, we'll probably keep track of the bounds. We would probably keep track of like this in the code. And at the very end, we can rebuild the substring. But for the purpose of the example, I'll just keep track of the length, 7. Okay, so now we move the left pointer to the right again. And now suddenly we've lost a $sign. So $sign gets decremented to 1. I'll put it in purple so you can see. 1 is not equal to 2. So we've lost a unique character count. So we can decrement this 4 to 3. And now we move the R forward. That means that in this substring here, we don't have all the characters. So we're going to move the R forward now to this $sign. We've got another $sign. So let's increment the $sign to 2. 2 is equal to 2. Here I'm going to start going a little bit faster because hopefully you're starting to pick up the technique. 2 is equal to 2. So we increment the unique character count back to 4. We can now start moving the left pointer because we have all of the characters. We have 4 characters found. So we move the left pointer to the right. E is not in our characters. So we lose an E, but we don't care. Here we had a substring of length, what was it? 1, 2, 3, 4, 5, 6, 7. But now suddenly we have a substring of length 6 here. 1, 2, 3, 4, 5, 6. So 6 is better than 7, so we can update our new best substring, or our new smallest substring, to length 6, and it's this one. Let me undo this. So I'll erase the 7 and put 6. And we're going to keep moving our left pointer to the right. We move it here. Now we've lost an F. So F goes down to 0 here. And once it's at 0, I guess let me make it in purple so that you can see that it's been decremented and it's no longer the same number of characters found. So we can decrement this 4 to a 3. And now, as you can see, we're going to have to keep moving the right pointer, and we will unfortunately never re-find an F. We'll find a C. That's not relevant. We'll find another dollar sign, so we will increment the dollar sign from 2 to 3. And eventually, there might be another example where, like, you would have an F, but you might have $3 signs, which would be fine. But the point is, we will never find another F. So at this point, we will finish out of our loop, right? We will stop our iteration or our traversal through this string, and we'll be done. And so we won't even bother moving the left pointer anymore because we know that like the right pointer is at the end of the string, and we don't have a substring here containing all the characters. So if we shorten the substring, we're not going to suddenly magically find the character or the missing character or characters. So we now have found our answer. It's a substring of length 6. And again, if we kept track of the bounds, we could rebuild that, and it would be this substring right here without the E. This substring right here, which is the answer right here. So as far as complexity analysis goes, the time complexity of this algorithm is really nice because, the naive way to solve this problem would have probably involved a lot of, double for loops or even triple for loops, maybe a lot of substring building where you're slicing substrings out of a string. But here we were able to very elegantly, use these two pointers, this sort of sliding window technique, to find this in linear time. So the time complexity is going to be O of B plus S, where B is the length of the big string and S is the length of the small string. The S comes from the fact that we are dumping everything in a hash table at the very beginning, so we have to iterate through all of the characters in S, so we have to do, a for loop of length S, if that makes sense. And then the B comes from the fact that we're moving our right pointer, so we're going to be moving our right pointer throughout the entire string. That's B right there. And then the left pointer, we'll be moving it, a few times throughout the string, but overall, like, you can very intuitively see that this left pointer the moving of this left pointer is never really gonna affect this B. At most we would maybe have like 2B if, for instance, our string were something like, I don't know, AA and our smaller string, and the big string was literally just a bunch of A's, and you can imagine that we would be moving, the right pointer by 2, and then probably the left pointer by 2 or by 1, and then the right pointer by 1. We would keep moving one at a time, but eventually it would only be 2B, and no matter how you put it, right, you will never get a far worse complexity than B. It will not affect it at the time complexity or complexity analysis level, if that makes sense. So the time complexity is going to be linear time, O of B plus S. And also, I guess, at every iteration, all we're doing are constant time checks, right? We're checking a hash table, values in a hash table, we're adding values together. It's very simple. And then the space complexity analysis, space complexity is going to be equal to the same thing, linear space, O of B plus S, because we are storing all of the characters in S in the smaller string in a hash table. And you can imagine that if all of the characters in the hash table were unique, then we would have a hash table of length S. And similarly, the big string might end up being identical to the small string. So like in the worst case scenario where the big string is identical to the small string, we are storing and has only unique characters, we are storing every character in a second hash table of length b. But in that case, it would be basically like 2b or 2s. Otherwise, we are giving we will be storing fewer characters. Like here, you could see we weren't storing C, we weren't storing D, we weren't storing E or X. But in that worst case, the weird edge case where the big string is equal to the small string and has unique characters, then we're storing a hash table of length B, and then at that point our substring would likely be of length B, but also of length S. So that's the space complexity. Overall, this algorithm is definitely not heavy on auxiliary space. So that's it for the conceptual overview. Hopefully you were able to kind of see the elegance of this sliding window technique with the 2 pointers. And now let's dive into the code walkthrough to see what it looks like. All right, so we've got our smallest substring containing function defined. It takes in a big string and a small string. And the first thing that we're going to want to do is to store every character, or rather all of the character counts of the small string in a hash table. So we're going to declare a variable called target char counts, char short for character, and we are going to make a helper function that actually creates this hash table. So get char counts is going to be our helper method, and it's going to take in the small string. This should be a very simple method to write out, so we'll do it right now. Get char counts, it takes in a string. So we'll declare a hash table, a char counts hash table, which will be a dictionary in Python or an object in JavaScript, however you want to implement your hash table. And we'll iterate through all of the characters in the string, for character in string. And here, since I'm actually going to be using this functionality of increasing or decreasing character counts in a hash table multiple times throughout my entire algorithm, and since depending on the language you use, this might not necessarily be a one-liner because you have to check if the character already exists in the hash table, I'm just going to create a couple of helper methods. Might be a little bit overkill, but I would explain this to my interviewer. I'm going to create 2 helper methods. One is going to be called increase char count, and it's going to take in a character as well as a char counts hash table. And this is just going to say, hey, if, let me write a pass here for now, if the character is not in char counts, then initialize it to 0. Char counts at character is equal to 0. Otherwise, char counts of character plus equal to 1. Again, depending on your language and depending on how you want to write your code, you might be able to make this a one-liner, but it might be a little bit hacky or a little bit less readable. I'd rather just make this into a helper method that is going to be very easily readable, where here I'm just going to say, hey, for a character in a string, instead of pass, just increase char count of character char counts. And I'll have a similar method here for decrease char count, which is going to take a character and char counts. And here I'll probably just assume that whenever I call this method, we already have the character in the hash table, because when is this going to be used? This is going to be used when we are moving the left pointer and kind of eliminating characters. So yeah, I'm going to assume that I don't need to do this check. So this is really just a one-liner. It's going to be char counts at char char minus equal 1. But again, these are all things that you would tell your interviewer. You would kind of explain to them what you're doing, why you're doing it. It's really the reasoning that matters more than what exactly you're doing for this. I would argue that you don't even have to write these out in an interview. You could probably tell your interviewer, hey, I would write increase char count and decrease char count. This is how I would sort of implement them. I would do the little check, these 2 lines. But for the sake of time, is it okay if I don't write it down? And they would probably say yes, and you can just use this on line 7 like I did here. Okay, and so in this method, we just eventually return char counts. So now we go back up to our main method, where we have gotten all of the character counts from our small string in a hash table, and now we're actually going to try to find the substring. So this is going to be the meat of the algorithm. Like I mentioned in the conceptual overview, we're probably going to be keeping track of the bounds of the substring so that we don't have to store random substrings. We don't have to slice substrings out of the string, which would affect our time complexity. So we're going to store the bounds, and we're going to call this substring bounds equals get substring bounds. This is going to be our main helper method, taking in the big string and the target car counts. Because remember, all that we needed, we no longer needed the small string. Once we have the character counts, the small string is effectively useless. We need the big string because we're going to be iterating through it, or through all the characters in it, and we need the target character counts. And then finally, I suppose we can do something like return get string from bounds, passing in the big string and the substring bounds. And this is going to be a helper method that we write at the end. Again, this is probably the kind of helper method that you could tell your interviewer, hey, do you want me to write this? It's very simple. You have your big string, you have substring bounds, which are just like a left and a right index, and you just have to slice that substring out of the big string. But yeah, that's something to tell your interviewer. Okay, so now we are going to write the get substring bounds method. Like I said, this is the main method of the algorithm, the most important one. It takes in a string, and it takes in target character counts. By the way, I realize that depending on your language, if you have types or whatever, you might not want to use the string variable. Maybe you would just use, str or something. But for Python, I'll write string. And so what do we want to declare here? There are a lot of things that we want to declare. If you remember from our conceptual overview, we are going to have a new hash table for the substring character counts, the character counts in the given substring. So we'll do substring car counts is going to be an empty dictionary, a hash table, and it's going to be the same format as this one, but we're just going to be building it sort of as we go. The second thing that we want to keep track of is we want to know how many unique characters there are in our string, in our small string. Remember, in the conceptual overview, in the top right corner of the screen, I had written it, we had 4 unique characters. And I said that was the number of keys in our character counts hash table. So here we'll do num unique cars equal len of target character counts dot keys. Right? So we get all the keys in the target character counts. This is going to be an O of n operation where n is the length of the small string. We get the length of the keys, the number of keys. That is the number of unique characters that we need. Then we're going to keep track of another variable. This is going to be the variable that we had in the top left corner of the conceptual overview, which is how many unique characters have we completely found? So unique characters done. I suppose for consistency's sake here, I should probably call num unique characters done. Num unique characters done equals 0, right? And if num unique characters equals 0, we're going to be incrementing this value throughout the algorithm, and we're going to try to find substrings where this value is suddenly equal to this value. Then we're going to have a left index and a right index. So there's a lot of setup for this algorithm. Left index is going to be equal to 0. Right index is going to be equal to 0. And now we can finally start with our actual algorithm where we iterate through the string. So we'll say while the right index is less than the length of the string. That's when we want to keep doing stuff. And let me give myself a little bit of space here. So while the right index is less than the length of the string, the right character, which is sort of the current character that we're looking at, is going to be equal to the string at the right index. If the right character is not in our target character counts, then we increment the right index and we continue. I'm sorry, here plus equal to 1. Why? Well, remember, when we were iterating through the big string in the conceptual overview, and we found, the character E or X that weren't in the characters that weren't in the small string or in the target character counts, we don't need to do anything. We don't need to keep track of those. We don't need to do anything. So let's just skip and continue and keep moving right index forward. If we arrive on line 23, though, then the right character is, whoops, I should have written in, then the right character is in the target character counts. And in this case, we want to increase the character count of this right character in our substring character counts. Because suddenly we have a right character that is relevant because it's in the target character counts, and it is in our substring between the left and right pointers, so we want to increase it here. So here I'm going to make use of my nice little overkill helper method. Increase car count, right car, and substring car counts. And so as you can see, again, this is why it's pretty useful. Otherwise, I would have had to rewrite like these three lines here, 38 through 40. I would have had to rewrite them here, whereas here I can write it in a clean one-liner that is very readable. Like I'm not doing anything hacky or something. It's very readable. Okay, so the next thing that we have to do is we have to check, hey, did we just fully find a unique character? Like remember when we had suddenly $2 signs, we were like, oh, we have $2 signs. That's the exact number of dollar signs in the target character count. So we have to increase that top left number that we had in the conceptual overview. So if substring car counts of the right character is equal to target car counts of the right character, then unique cars done, num unique cars done, plus equal 1. If the number of characters of this right car in our substring car counts is equal to the 1 in the target car counts, then we have fully found that number. And we can increase the number of unique characters done by 1. And this now lets us do the next major piece of logic, which is moving the left pointer. When do we move the left pointer? We move it when we have num unique characters done equal to the num unique characters. When the number of unique characters in the substring we've found is equal to the number of unique characters in the target substring, or in the smaller string, then we want to move that left pointer. So the way we'll do that is with another while loop, where we're going to say, while the unique characters, or the number of unique characters done, is equal to the number of unique characters, right? Because so long as this holds true, we want to try to shorten the substring and make the left string smaller. So long as this holds true, and of course, let's make sure that our left index is still, smaller than or equal to our right index. We never want to get to a point where like our substring is a string of length, 0 or -1 or something that doesn't make sense. So long as this condition holds, this, by the way, this while, the first condition of the while almost serves as an if statement. Hey, if we found all the characters, and so long as we keep having the same characters, then do this. So what do we do here? Well, the first thing is we want to see if we can update the substring, because maybe we have a shorter substring. So here, actually, I should probably declare a variable up here called substring bounds, and this is going to be equal to the bounds of our substring. So we're going to have an array, and here we're probably going to have to handle the edge case where there is no substring. So the way we'll do it is we'll have the bounds start at 0 and end at float infinity. Float infinity. I'm writing the wrong parentheses, the wrong brackets. And at the very end, we can do a check where we say, hey, if we're still dealing with infinity, then just return, the empty string because we don't have a substring. But so here now what we'll do is we'll write a helper method that tells us whether or not the new substring bounds lead to a smaller substring. So we'll do substring bounds equals get closer bounds, or get, the shortest substring bounds. And we'll pass in the left index, we'll pass in the right index, we'll pass in our substring bounds at index 0, and our substring bounds at index 1. And this is going to be a very boring function. I'll write it right now. A very boring function that you can usually tell your interviewer, ask them if you don't have to write it. And so this is going to say, hey, we take in 4 indices, index 1, index 2, index 3, index 4, and we return index 1, index 2 if index 2 minus index 1 is smaller than index 4 minus index 3, else we return index 3, index 4. Let me make sure that I wrote that correctly. So we say, hey, we've got 2 pairs of indices. If index 2 minus index 1, so the distance between these 2 indices, is smaller than the distance between these 2 indices, then we return 1, 2. Otherwise, we return 3, 4. So we use a ternary operator here, and this gets us the smallest substring bounds. This is basically the way that we say, hey, we have a smaller substring. Here, the substring bounds have a distance of 6 instead of 7 or instead of 8, like we had in the conceptual overview. Okay, so once we've done that, we can say, now we have to see if we can move the left index forward and if we are going to be losing characters and so on and so forth. So we can say left character is equal to string at left index. If the left character is not in the target car counts, then we just increment the left index by 1 and we continue. This is exactly the same, these 3 lines are exactly the same logic as we had here. If we're shortening the string with the left character and we see that, oh, we just moved the left character to the right and we lost a character like the character X that wasn't in our small string, okay, cool. We don't need to do anything. Just keep continuing. This condition here is going to keep holding true, and let's just see if we can continue shortening the string. On the other hand, if we don't get into this if condition, so if the left character is in the target character counts, that means that we're about to lose that character. So what we have to do is we have to say, if the substring character counts of the left character are equal to the target character counts of the left character, then the unique characters done, the number of unique characters done, is going to minus equal 1. This is exactly the opposite of what we're doing, these 2 lines, on lines 25 and 26. If the character that we were at, let's say it was the $, and the substring character counts, was equal to the number of counts in the target character counts, then that means that we're about to lose one of the unique characters fully done. And we have to decrement that value in the top left corner that we had in the conceptual overview. Notice that this is an equal. It's possible that we had $3 and the target character counts was only $2. So here we wouldn't reduce that because we would be going down from 3 to 2, but we'd still be good. But here, no matter what, on line 35, we're going to do decrease character count of left character and substring character counts, right? So we decrease the character count of, let's say, the $, from 3 to 2. And this is our nice little overkill helper method here, where again, the way our algorithm is written, we have the implicit assumption that we know this left character is found in this hash table. We know it's found there, so we don't need to do this double checking here. To be honest, in production code, we probably should do the checking because, we shouldn't make these kinds of assumptions, but for the sake of this, I think it's fine here. And finally, we can increase the left index by 1, keep moving the left index forward, and that's it. That's it for this inner while loop. Eventually, we will break out of this condition. To be honest, if we ever hit this, line 33, 34, we will, or line 34 rather, we will break out of the while loop afterwards, and that's that. And so then here under this while loop, now we want to increment the right index, so right index plus equal to 1. So as you can see, it's weird. This algorithm is these while loops, this inner while loop is a very similar version of this outer while loop. where we do sort of almost like the same thing, but the opposite thing in some cases, because we are moving the same pointers in the same direction, and we have to do the same sort of checks, but sometimes we decrement, sometimes we increment, depending on the left or right pointer. And that's it. Here, once we're out of this while loop, we will eventually have gotten to a point where the right index is past the length of the string, and here we can return the substring bounds that we've found and that we've continuously updated. Where did we update them? Here. And I think that's it for the algorithm. I think that now we have all of the methods and we're good. Oh no, we didn't write the we didn't write the get string from bounds, which is this. So let's write it really quickly. So get string from bounds. So what is this going to look like? We take in a big string and substring bounds. So we'll make this more scalable with just string, or it doesn't have to know about a big string. Let's just call it string and random bounds. And we are going to say, okay, start end equals bounds. And, I guess here we have to handle the edge case where we're dealing with float infinity. So if end is equal to float infinity. And here, by the way, you don't have to use float infinity. You don't have to use like infinity or the maximum number in your language. You could use whatever you want. I think that makes sense for me. But maybe you want to store maybe you want to store another variable, a Boolean, that says whether or not you've found a substring. Up to you. But so if end equals to float infinity, then we return the empty string. And otherwise, we return the string where we slice it from start to end plus 1. Start to end plus 1. Because remember, this is always excluded, so we want to capture that end index. And now we have actually finished our algorithm. So this is going to run in O of B plus S time and O of B plus S space. We covered this in depth in the conceptual overview of the algorithm. The S comes from the fact that we are creating this target character counts hash table in O of S time, because we just iterate through the entire string. S is the length of the smaller string, and we're storing at most, S characters. And then B is going to come from the fact that our while loop here is certainly going to go through the entire big string. The inner while loop is never, you can sort of intuitively see that it'll never really affect the complexity analysis, the time complexity at a meaningful level. It'll, maybe make it at most like 2b or something, but it will never affect it at a meaningful level. It would never be like b squared or something. And the S time comes from the fact that, the B space comes from the fact that our substring character counts or our final substring might be of length B in some edge case. Typically, it's not going to be of length B, but it might be in the case where the big string is like equal to the small string and has all unique characters. And that's it. Just to reiterate very quickly, we get all the character counts of the small string in a hash table. Then we get all of the substring bounds by, iterating with 2 pointers, where we always say, hey, if we ever have our right character that's in the target character counts, increase it in the substring character counts. If we're at a point where the substring character counts are equal to the target character counts for that character, increase the number of unique characters that we have that are done, that are fully counted. If we're ever at a case where the number of unique characters fully counted is equal to the number of unique characters in the small string, and so long as we remain that way, keep moving the left pointer until it maybe surpasses the right pointer, in which case we want to stop doing that. Try to update the smallest substring by doing this little comparison here. Compare the left and right index that we currently have to whatever we currently have in the substring bounds. If we're ever at a point where the character at the left pointer is in our target character counts, and we happen to have the same number up until now of that character in the substring and in the target character counts, Then we decrement the number of unique characters done because we're about to lose that character. Always decrease the character count of that left character if it was in the target counts. Always decrease it from the substring character counts. And keep moving like that until you return the substring bounds when you're done iterating through the big string. And the substring bounds just take care of the edge case of infinity, meaning there is no substring, and then return a slicing of the substring. So that's it for this question. It's a pretty tough one, and it's a very cool one. I think this technique is very useful. It is certainly useful in other problems. There are a couple of other problems, I think, where you can use it on AlgoExpert. You may have noticed it already. And that's that. I hope this video was informative, and I'll see you in the next video.